However, you should ask your school authorities.
1928, USA. The telegraph service across the Atlantic experiences interference. Messages sent using radio signals get corrupted by other kinds of noise, much like a hiss of a transistor set. A young staffer named Karl Jansky is put on the job of investigating these disturbances. In his search, he builds a special device. What it discovers will forever change how we study the cosmos. How did a simple radio receiver alter the course of astronomy? That's a question of science. What comes to your mind when you hear the word radio? To most of us, radio means transistor sets that transmit information and entertainment straight into our ears with a single touch of a button or turn of the knob. But radio actually refers to electromagnetic waves that are picked up by the transistor. These are radio waves similar to the most familiar kind of electromagnetic radiation, visible light. Unlike visible light, radio waves can't be seen by the human eye, but they can be useful in other ways, such as bringing your favorite radio channel to your transistor set. But in the 1930s, one scientist discovered that radio receivers had another extraordinary use. In 1933, Karl Jansky, an engineer tasked with studying radio interference, announced the discovery of a new type of radio signal. It had been captured by an instrument he'd built known as the merry-go-round. It was a radio receiver that revolved on a turntable and recorded signals at 20.5 megahertz. Jansky announced that the signals it received were coming from the Earth's home galaxy, the Milky Way. This was a stunning discovery. It suggested that celestial objects were actually radio sources, emitting radio signals that could be picked up by receivers on Earth. So far, objects in space had been studied using optical telescopes and visible light. But Jansky's discovery meant that we could study the cosmos using something else. Radio receivers tailor-made for astronomy. In other words, radio telescopes. Unfortunately, Jansky himself was unable to continue what he'd started because of the outbreak of World War II. So the mantle was picked up by a ham radio operator and engineer called Groter Reber. Reber embarked on an ambitious project to build the first ever radio telescope in his own backyard. He began mapping radio waves from the Milky Way and the nearby galaxies. By the 1940s, his publications and studies had inspired many others like him, and the field of radio astronomy was here to stay. But how exactly is radio astronomy different from optical astronomy? These are images captured by optical telescopes most of us are familiar with. Even amateur astronomers would recognize these as the Sun, the planets Jupiter and Saturn, and the Milky Way. But what happens when we look through a radio telescope? The same objects reveal a completely new character. In this radio universe, the same objects appear more active, changeable, and violent than their optical avatars. Sometimes, this radio universe even reveals phenomena for the very first time. Through the 1940s, 50s, and 60s, many new objects were discovered by radio telescopes. Objects like pulsars, quasars, and exotic radio galaxies. Happening mostly in the West, These early discoveries were being closely followed by a young student in post-independence India.
I was taught by K.S. Krishnan, who was one of the authors of the papers which brought C.V. Raman Nobel Prize. He had gone to Australia in 1952, some international meeting. There he saw remarkable discoveries being made by relatively simple equipment. He gave a talk at National Physical Laboratory and I got very interested.
In 1963, Govind Swarup was handpicked by Homi Bhabha to form India's first radio astronomy group at the Tata Institute of Fundamental Research. Swarup immediately approached him with a novel idea.
I considered if we can make a big parabolic cylinder on a release slope with parallel to axis of Earth. And Bhabha, I met him and he questioned for half an hour, 1 hour. Fortunately, I had answers. And I said, shall I write a project proposal? So young men, form a team. Once form a team, we'll approve your project. So therefore, in a hurry, we built the Kalyan Radio Telescope.
The Kalyan telescope was India's first radio telescope. It was built using receiver dishes donated by Australia. Its aim, to study the sun as a radio source. The Kalyan telescope's construction and performance consolidated the Indian Radio Astronomy Group and impressed Homi Bhabha. So in 1969, Bhabha commissioned an even bigger project, a cylindrical radio telescope that sat along the slopes of Ooty in Tamil Nadu. Swarup's novel design made it possible to build a very large telescope at very low cost. Its location also made it structurally stable as it rotated from east to west, following celestial objects up to 10 hours at a time. The Ooty Radio Telescope was built entirely in India, using Indian design, components and technology. Till date, it remains one of the most sensitive radio telescopes in the world, thanks to its unique location and large size. The Ooty telescope gave Indians a sophisticated, world-class instrument in their own country. It would allow them to participate in some of science's biggest quests, such as the debate between the Big Bang and steady-state theories. As this dilemma became resolved in the 1980s, Govind Swarup set his eyes on the next big goal: to reach out so deep into the radio sky that one could study the very foundations of our universe.
According to Big Bang, before the stars and galaxies, there were only massive neutral hydrogen clouds. And the universe was only some seconds or minutes away, 75% hydrogen, 25% helium. So therefore, it occurred to me, can we build a radio telescope to find massive hydrogen clouds before stars and galaxies? We had a group, we had technology. Can we do something bigger?
80 kilometers away from the bustling city of Pune, in the open fields of district Kodad, and sprawled across 25 kilometers, is the Giant Meter Wave Radio Telescope, or GMRT. This is the realization of Indian radio astronomy's most ambitious dream. The GMRT is a collection of 30 massive dish antennae which collect radio signals coming from faraway objects and phenomena in the sky. It is one of the world's most sensitive telescopes to capture radio signals measured in meter-long wavelengths. Since it's the only one of its kind in this part of the globe, the GMRT provides a view of the sky that is completely unique.
There's a growing need, global need, to build a large instrument at low frequencies which can probe the universe at these wavelengths and discover new things. And that's how the GMRT was then conceived.
When you think of a telescope, you don't quite imagine the GMRT. There is no viewfinder to peep through and no optical lens to sweep across the sky. Instead, there are giant parabolic dishes made of wire mesh, supporting a radio receiver at its focus. How does it all work? Each dish is turned towards a radio source in the sky, the signals from the source are collected in its bowl-like structure and directed towards the radio receiver. From here, the weak signals are strengthened by amplifiers and sent via optical cables to the GMRT's supercomputing digital systems. The digital systems process the radio signals, but they don't immediately give astronomers a visual image. Instead of the image of a celestial object, there are reams of numbers. Now, it's up to the astronomers and special software to convert this numerical data into an image of the radio emission from the source. But why does the GMRT need 30 individual dishes to get the job done? The GMRT is an interferometer. That means it collects radio waves from multiple dishes and combines them intelligently to construct the whole. For this, the GMRT uses a special interferometry technique known as aperture synthesis. It's a technique that earned its developer, Martin Ryle, a Nobel Prize in 1974. Aperture synthesis relies on mathematical computation to account for factors like distance between each dish, angular differences, and the Earth's rotation, etc., to give out a complete idea about the radio source. By correcting for these factors and combining the data, 30 individual dishes spread out across 25 kilometers can behave like one giant dish that's 25 kilometers in diameter. Having 30 such large dishes also means that we can collect many more radio waves, and hence we are able to see very faint objects. This makes the GMRT one of the largest telescopes in the meter wavelength, giving the GMRT its giant radio telescope status. The GMRT's dishes are arranged in a Y shape, with 12 dishes in the center and the remaining 18 fanning out along 3 branches.
You have to combine signals from the antennas in a pairwise fashion in what is called a correlator, and each pair that you make from the available antennas gives you one piece of information about the image in the sky. By combining the signals from all of these antennas in real time, by bringing them back to the central observatory and doing the correlations, you can actually make an image of an object in the sky where the resolution is that what you would achieve with a 30-kilometer size antenna.
What did this type of array need to be built? First, it needed a large area to spread out across. This area had to be as free of radio interference as possible. In other words, it had to be in a noise-free zone without mobile phone signals, television signals, and even high-voltage electricity interference. Most importantly, the GMRT needed a team of enthusiastic astronomers and engineers to design and build the entire array from scratch. In the 1980s and 90s, India was uniquely equipped with all these. Imagine building a radio telescope without any technological assistance from countries who had built such instruments before, well before the age of the internet.
We had not built that at Ooty. Ooty was a relatively simple single antenna, but the basic know-how was there. Once the basic know-how, you can build up. Okay, today is much easier. Google has a lot of knowledge, but those years, a lot of bright people joined us, and most electronics were done by people 22, 25, 27 years age.
Professor Swaroop and his team had to come up with an entirely original, indigenous design. They established themselves as the National Center for Radio Astrophysics and roped in the help of Tata Consulting engineers and scientists from the Raman Research Institute. While the team was well experienced, the task at hand was daunting. Almost immediately, one of the biggest challenges confronting them was how to build lightweight dishes that were strong enough to withstand high wind speeds and still be cost-effective to construct. The design group quite literally got smart by inventing SMART, or stretched mesh attached to rope trusses. This design approach gave the GMRT giant 45-meter dishes that only weighed 100 tons. But this wasn't the only novel decision Professor Swaroop and his team took. Their next challenge was, having designed the dishes, how would they connect this 25-kilometer network to the main building?
I came to know optical fibers development is there. So we have antennas far away, we can join them by optical fibers.
At the time, no other interferometer array had ever used optical fiber cabling. But the gambit paid off so well that it set a global trend.
Today, that is the norm. Almost all radio telescopes, it's unthinkable to not have optical fibers to link the different antennas.
Through the 90s, the elements of the GMRT began to come together. 30 dishes sprouted up across Khodad district, meticulously pieced together by engineers, technicians and laborers working hard shifts. Even as the GMRT began to take shape in the fields, other teams got busy designing the electronics. The electronics of a mega science instrument like the GMRT can get rather complex. They're required to handle extremely large amounts of data coming in from each dish. All this computing has to happen at extremely fast rates, which means the electronics have to be absolutely cutting edge.
So the electronics is fairly sophisticated, and although there's some experience within the group from the building of earlier telescopes like the UTI telescope, there were still many new hurdles and challenges that had to be overcome. For example, the big digital backend, which is called the correlator, that had to be built was a major challenge.
After long years of brainstorming, innovation and painstaking hard work, the GMRT was commissioned in 1998. Initially set up only for Indian scientists to use, by 2000 it was internationalized, drawing in astronomers and astrophysicists from every corner of the country and globe.
This has come to occupy a place where half of the observing time of the telescope is taken up by competitive means by astronomers from outside the country. 30 countries, I think, are represented in the usership of this telescope.
What makes the GMRT such a sought-after instrument? It's one of the most sensitive telescopes that functions in the low-frequency range, sweeping from 150 MHz to 1450 MHz, with two feeds in the 1665 MHz range. At this range, astronomers get a rather exclusive peek of the universe. Researchers cover a diversity of topics, including exotic objects like pulsars, quasars, and radio galaxies, objects only seen in radio. Others study the sun, solar winds, and planets, both within our solar system and beyond. Many use the online TIFR GMRT Sky Survey from the comfort of their own cities to study the entire sky at 150 MHz. And some even come to make extraordinary discoveries.
One of the stars we investigated, it is the largest radio galaxy in the universe. So it means not only radio galaxy, but also largest single object in the universe. It is 5 megaparsec in size, so it's really large.
Since the GMRT offers a unique service to astronomers, it's houseful around the year. But not everyone can get in. Astronomers must submit a detailed proposal of their study. If selected, they are invited to the GMRT. And then, the reins are handed over to the central control room. As the name suggests, this is the place from which all activities of the GMRT are controlled.
So this control room is being run 24 hours, 365 days, more like similar to air traffic control. And observations also happens round the clock all through the year and all through the days.
The central control room instructs the different antennae in the array to point at the exact spot in the sky where the observation needs to be made. In the open fields, the dishes begin to turn.
Main function of the dish is to point anywhere in the sky. In order to achieve that, we have two axes of rotation. One is the azimuth axis, where the axis of rotation, the axis is perpendicular to the plane of the earth. In elevation axis, the antenna moves in such a way that the axis is parallel to the earth. So it is possible for you to cover the sky from horizon to zenith.
Once fixed, the dish collects radio signals and converges them at its focus. Here, different types of radio wave receivers or feeds rotate on the command of the central control room. The signals coming from the cosmos are from so far away that their journey has significantly weakened them. And so, they need to be amplified before they travel onwards to the main computing systems. Throughout this journey, the signals are under constant threat of radio interference.
We have selected this area in such a way that we are far away from industries, we are far away from Mumbai and Pune traffic or industries, and all our mobile towers which is in and around, they do not operate in our GMRT band. Plus there are things like electrical power lines, they also contribute noise to this GMRT. So those things also regularly cleaned, that they do not produce any interference to the GMRT signal.
Even after filtering out the noise, there's an incredible amount of data coming from each dish. This data is passed through a digital system called the correlator. This is where the interferometry technique of aperture synthesis is put into practice so that the astronomers can get the information they require.
So this is a new generation of technology which allows you to do all the complicated digital signal processing on general purpose computers which are connected together with very intelligently written software which optimizes and gives you the maximum performance from these machines so that you can meet the requirements for the signal processing. So this is a fairly sophisticated piece of hardware. It is probably one of the first observatories which has a fully real-time software backend running 24/7 servicing a 30 antenna telescope.
More than 10 years after the GMRT first started, hundreds of astronomers have walked away with incredible observations, each one bringing us a little closer to understanding the universe we live in. And so, to keep up with our ever-growing hunger for knowledge, the GMRT is now upgrading to the next level of technological capability.
Today, the GMRT is being upgraded in a manner which will increase its performance by a very large factor. And one of the most important things that we are doing is to increase the frequency coverage. All of this entails a major change in the entire receiver chain of GMRT.
The same independent spirit that built the GMRT is driving the upgrades. Indigenous technology and engineering solutions are renewing every aspect from small to big. The dishes are being reinforced against natural enemies like wind and rust. The mechanical systems like motors are getting smaller, lighter, and more efficient. Radio receivers are being rehauled for increased sensitivity. Electrical and electronic systems are being redesigned to reduce radio interference even more than before. And the digital backend is entering a new paradigm of intelligence. When completed, the new and improved GMRT will offer astronomers an even more powerful window into the radio universe. But the project that began as an audacious dream won't just end there.
There is a whole lot of very basic physics stuff which GMRT hopes to answer. So all this will enable new kind of science which was not possible till recently.
Once you want to fly to the moon, you will find the ways to do it. So you have to have a large challenge. Once the challenge is there, you start finding solutions.
If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.